Hey guys, today we got complex zeros and the fundamental theorem of algebra. Complex zeros and fundamental theorem of algebra. I know it's what you've always waited for. All right, the fundamental theorem of algebra first says every polynomial, like every polynomial, not just some of them, but every one that has some kind of degree n, if n is bigger than 1, with complex coefficients, meaning real numbers or imaginary, has at least one complex zero. Now, that doesn't mean it's an imaginary zero. It means it has a zero. So every polynomial has either a real answer, negative or imaginary answer, some kind of zero. All right. Also, we're going to see some complete factorizations today. Some factorizations you're not used to seeing. Complete factorizations includes complex numbers being included in the factors, which you haven't seen before. So that would be the new thing today. So let's look at a couple here. All right, this says that p of x equals x cubed minus 3x squared plus x minus 3. And part A says find all the zeros, and part B says find the complete factorization of function p. So looking at that one, it looks like it factors by grouping. Let's just factor by grouping. Let's take the first two. Let's take out the x squared. That leaves an x minus 3, which just so happens to be what the second part is, x minus 3. So factor by grouping, I'm going to take out this x minus 3. When I do that, that leaves an x squared here, a plus 1 in the front. And used to, we would stop right there and say, okay, that's completely factored. But it's not. So let's do this. First part says find all the zeros. One of my zeros is 3. Okay, so there's one of them. That comes from that parentheses right there. What I'm going to do to find the other two is I'm going to take that x squared plus 1, bring it over here to the side, solve it, move the 1 over, take the square root. Remember, the square root of negative 1 is plus or minus I. So there's my zeros right there. 3 and plus or minus I. Those are my zeros. So to factor completely, what I'm going to do is I'm going to keep this x minus 3, and that x squared plus 1, because the zeros were I and negative I, I'm going to write it like this, x minus I, x plus I. I'll probably put the I for the plus sign. And there it is. There's the complete factorization. So finding the zeros allows you to write the complete factorization of that, even though you're not used to factoring with imaginary numbers. That's the new thing. All right, we're going to do the same thing with this one. This one says x cubed minus 2x plus 4. So I'm going to roll with that one here. First of all, that's not a factoring method that we know. All right, so I'm going to go ahead and do what we did the other day. Make a little list. My possibilities are 1, 2, and 4 if I make my list for what the zeros could possibly be. And just to save some time, I'm gonna kind of peek ahead, see which one works. I think the negative 2 does. So let's try negative 2 in here, which give me 1, negative 2. Oops, forgot my 0 right there. 1, 0, negative 2, 4. Put down the 1, negative 2, that's 4, that's 2, that's negative 4, perfect. So that gives me this. That gives me x squared minus 2x plus 2. And that right here, there are no factors of 2 that add up to be 2. So that means I'm going to have to either do quadratic formula or complete the square. Let's do quadratic real quick. X equals negative b plus or minus the square root b squared minus 4ac all over 2a, which is 2. So I get this. I get 2 plus or minus inside there. I get negative 4 over 2, which is 2 plus or minus 2i over 2. And if I reduce that even further, I can take out the 2's. It just gives me 1 plus or minus I. So my zeros are those two. Okay, those are my zeros. So if I'm going to write the complete factorization, I'm going to go with x. This is going to look crazy when you see this. Let me pull this up a little bit, make it a little smaller. But that's okay. All right, so here it goes. P of x equals negative 2 is a 0. Negative 2 would be this factor. It would be x plus 2, the opposite of what it says. Now, this is where it's going to look a little different to you. My other two zeros are 1 plus I and 1 minus I. So I'm going to write x minus 1 plus I. That's actually a factor because 1 plus I is the factor. And I'm also going to write x minus 1 minus I like that. And then just to simplify just a little bit more, I know you're like, what even more? Yeah, just distribute the minus signs. That minus sign right here is going to make that a minus 1 minus I. And the minus sign right here is going to make that minus 1 plus I. Okay, so that right there, that's the complete factorization. So we're finding zeros first, like we did before, and then we're using that to write the complete factorization. All right, zeros theorem. Every polynomial of degree bigger than 1 has exactly n zeros. So whatever the degree is, that's how many zeros it has, provided that a zero of multiplicity k is counted k times. So that's kind of a new word for us, multiplicity. Multiplicity is how many times a certain zero occurs. I'll put an example down here. This one's already factored out for us. Looks really nice. Look at the exponents first of all. I got a 3, a 2, and a 5. If you add those up, that's 10. That means the degree is 10. The biggest exponent is 10. I should have 10 zeros. But if you notice, there's only 3. But what we're going to say is that's come from this parentheses. 1 is a 0, but we're going to say it has multiplicity. I'm not going to write the whole word. I'm going to put multiplicity 3 because it occurs 3 times. Negative 2 is a 0 with a multiplicity of 2 because it occurs 2 times. The exponent is 2. Negative 3 has a multiplicity of 5 because it occurs 5 times. So if you add all those up, that's 10, which is the degree. Okay, so whatever your degree is, your biggest exponent, that's how many zeros you're going to find, as long as you include the multiplicity. Okay, let me show you one more. It says find the complete factorization in all 5 zeros. This one has 5 zeros. So first thing I notice when I start this thing is it has a GCF. I can pull out the 3x. If I pull out the 3x, that's going to leave an x to the 4th plus 8x squared plus 16. All right, so I'm going to keep trying to factor that some more. I think that's going to be x squared plus 4 and x squared plus 4 because 4 times 4 is 16, 4 plus 4 is 8. That works really great. So before I can find the complete factorization, I need to completely factor. So I'm going to break down that x squared plus 4. That's a pretty easy one. X squared plus 4 is 0. Move the 4 over. It's negative 4. Take the square root. Plus or minus 2i is your... So those are the zeros there. So I'm going to say 3x, x plus 2i, x minus 2. By the way, your 2i's, you're going to find out as you go through this, and you're going to start seeing some patterns develop. When you have an x squared plus 4, that's a sum of squares. It's a sum of squares, and you can now factor sum of squares using i's. This was the same factor, so I'm going to put the same thing, x plus 2i, x minus 2i. I'm running into my problem there. Okay, so here's what I have. Completely factored. I got 3x, and I have x plus 2i squared, and x minus 2i squared, and squares are a big deal. So there's the complete factorization. The zeros would be 0 from right here, negative 2i with multiplicity 2 because it's got an exponent 2, positive 2i with multiplicity 2. So I started with x to the 5th, end up down here with 1, 2, 3, 4, 5 zeros, which is what I wanted because of the multiplicity. All right, I know that's kind of new word. We'll work on it a lot tomorrow when you come in. Can't wait to see you, and see you then.